This morning, before the lunch break, we stopped in terms of where we are going to start. I explained to you what we are going to do this afternoon. We are going to talk about mechanical properties of food materials. It's all about elastic nature of the material. Uh, when I say elastic nature, we are talking about the solid food material, not liquid food material. So that's what we are going to discuss this afternoon. So when you look at the mechanical properties, it's also part of the rheological properties. Uh, some people differentiate. Some people say rheology means study of flow and deformation together. But some people will not say this is a rheological property. They'll probably say mechanical properties only. So for the purpose of this workshop, we can consider both the mechanical properties also rheological property. Mechanical property is one of the rheological property because rheology is all about study and flow of material, study of flow and deformation of the material. So, but mostly we'll talk about the deformation here. So what is rheology again? It's rheology, study of deformation and flow. We all know that. And in Greek terms, rheo means flow or current or stream. That's what the rheo means. So that's how the rheology came. You all know that when you look at the rheology, how old the rheology is. Any thoughts? Is it 50-year-old, 100-year-old, 200-year-old? Any idea? Anybody has any idea? In terms of the food material, rheology is borrowed technology or borrowed phenomena we studied. So it dates back to 50 years back, 1970. People started talking about rheology of food material, mechanical properties of food material like that. Before that, nobody knew about anything. Nobody even studied about that. That time it was just a material, that's all they cared about it. There was no scientific knowledge or scientific study of this material in terms of rheology. So it's only 50 years old because all the technologies we are currently applying in food materials, everything is borrowed studies. When people know about the polymers, people know about the rheology of polymers, and everything is borrowed from polymer field to the food material. So that is something, it's very relatively newer phenomena. People started looking at it. We all know that solids will deform and the fluids will flow. So this information is very important when we start talking about the mechanical properties. Again, rheology is nothing but study of deformation and flow of a material. It started back in 1970. The applications of this concept and the theories, they are all in every facet of the food and biological sciences industry. Now this has been grown very, very extensively, and it has mushroomed to a lot of new technologies, new way of looking at things. So there are thousands of studies coming up every year in this field. A lot of new advancement also in here. So that's what we are going to talk about down the road. So analysis of rheology will be different for liquids and solids foods because solids deform, liquids flow. So biological material can behave as solid, which is elastic, or fluid, which is viscous. So now we are going to concentrate mostly on the elastic nature of the material, which is the solid material. Tomorrow we'll talk about the viscous nature of the material, which are mostly fluids. And also it's a biological material. So any food material, it's not purely elastic nor purely viscous, right? What would be the purely elastic material? When you think about the solid material, what are the materials which are purely elastic?
So how much can it stretch? It cannot be break.
Okay. Say it again. Your name? Moshmi? Okay. Moshmi says that materials will be keep how much it is stretched, but it cannot break. So those are all elastic material. Okay. Do you everybody agree with that statement? What she is saying is materials keep deforming.
Exact shape. I mean, it cannot get longer or shorter. When it stretch, then
It will not deform.
form.
It regains its original position after stretching.
Correct. It regains its original position after stretching. Or on the other hand, if you compress the material and if you release the force you apply, this will come back to the original shape. That's called the purely elastic material. Classic example for a purely elastic material is what? Spring. The spring, how much load you apply, it will compress. Once you release that much force out, that will come back to the original position. Food materials are not elastic material. If it is elastic material, nobody will be eating any food material, right? Because there is no viscous nature. Viscous nature will come from the moisture, fat, things like that. So if the material is purely elastic, for example, if it is purely made of protein structure, you cannot eat that, right? It won't be palatable. That is the bottom line. So it's always a mixture of elastic nature and viscous nature. So whatever information we are going to study now, it's assuming that we are going to consider the food material as a elastic material. We are going to consider whatever concept we are going to apply, we are going to assume it is behaving as elastic material. So whatever things we study now, we are going to assume it's elastic, and so it's always apparent something. It's not absolute something. It's apparent of something. So that is a different. So you need to understand that. So with the grain of salt, we are going to look at the biological material and how we can measure the mechanical properties of this biological material or any food material. Okay, let's turn our discussion to biological material. Do you all agree that any food material is biological material? Yes, 100%? Okay, so we are in agreement, any food material is a biological material. Can food material consider as a biomaterial? What is the difference between biomaterial and biological material? Just give it a thought for a second, then we will discuss why biomaterials are not biological material or they are the biological material.
So biomaterials.
Go ahead, please.
Biomaterials may be those materials that are made up from the biological, like enzymes we are getting it from some bacteria. Those are biological things, but the enzyme is not biological, it's a bio.
Okay, she thinks that enzymes we create from the biological material are not biological material, but they are biomaterial. That's what you are thinking? Yeah. I'm not sure about that because I'm not expert in enzymes and things like that, but enzymes are also biological material. The biomaterials are the one which are engineered material. For example, if something goes wrong with your teeth, and then they try to put a new teeth into that, that new teeth may come from biomaterial. It may be a mimicking the actual teeth. The another example is, if you break your bone, they try to replace it with some steel or some other material. Those are all biomaterial. They do not come from the biological source. That's why it's called biomaterials. But sometimes people use both the terminology for our food material, biological material. So biological materials are different than the biomaterial. From our discussion point of view, that's what I want to make sure that you all understand what's the difference between biomaterial and biological material. Biomaterials are primarily synthetic material which doesn't come from the biological material. Any thoughts on that? Any other discussion anybody would like to make? Okay, everybody on the same page? So for our discussion, we will talk, whenever we deal with the food material, we will think about it as a biological material, not as a biomaterial. That's how we differentiate. So basically, any food material is a combination of solid and fluid, which is why it's called viscoelastic material. And that is a classic example for the dynamic rheology study. You all know the dynamic rheology, right? Dynamic rheology? Okay, that's okay. I mean, it's a good thing that you are not familiar with that. We will be talking about that down the road, but I just want to throw that idea now so that we know that we will be studying about the dynamic rheology, which is all about the viscoelastic nature of the material. Okay, now let's look at the deformation and flow of solids. Okay, deformation and flow of solids. So, in classical example is, typically what happens? You put material in your mouth and you try to bite it. When we say biting, what we actually do? You are compressing the material, knowingly or unknowingly. When you are biting things, this may not happen only the biting, only compression. There could be compression, there could be shearing of the material, and that could be flow of the material happening within the mouth. So all these things, all the overall processing happening within the one food material going into our mouth, between the teeth. So it's called a uniaxial compression. You understand what's a uniaxial compression means, right? So food material is 3D material, but we do only apply the force in only one axis. We don't apply force in all three axes, right? Because then it gets complicated, right? Because you apply one dimension, another dimension. If you do that, then we do not know where it is deforming. If you do one dimension, one uniaxial compression, then you can follow how the material deform. That's what called uniaxial compression. So basically, when you do that, you are looking at the force required to reach a certain deformation. In classical compression test, what do? You deform the material and you measure the force. Follow me? You do not apply the force and then measure the deformation. You deform the material and simultaneously you also measure the force you apply as you deform the material. And that is how data you collect, force with respect to deformation. Follow me? On the other hand, if you have material and then you put only small amount of force on top of that, small amount of load, so what happens that time when you do that? It's a constant force you are applying and you are going to measure the deformation. So when you put the constant force, material will start flowing slowly and then it will stop deforming after some time. And from that measurement, that's called creep, material creeping with the constant force. We will be talking about that also. So in uniaxial compression, it's a force recovered. So you are monitoring the force as you deform the material. In classical compression test, that's what we do. So in this case, what size and shape of the material will I use? Let's say some farmer, he has a apple orchard and he has different varieties of apple he is growing, and he want to find out when this apple will get matured, then he can send it to the market for distributing to the consumer. That's an example. In this example, he would like to know how we can measure the maturity of the apple. So one way to measure the maturity is measuring the force required to deform in a uniaxial compression test. So here, what kind of sample he need to use so that he can measure the maturity, or at least monitor the maturity for different samples. So how he can prepare the sample? What kind of sample he need to use? Can he just put the one whole apple there and then compress it? Pardon me? Random samples to be taken, meaning that what he is saying is random samples should be taken, which is true. Any sample we try to do, we have to do random sampling. But can we put the whole apple in the compression test in the machine where you can measure the force required for a small deformation? Can he do that? Okay, you can cut. So what's your name? Pooja. Pooja is saying that you can cut the sample into cube and then you can compress a sample on one axis and measure the deformation in other axes. That's one way to do that. Okay. How uniform this cubicle can be obtained? It's easy to obtain a cubical sample. What would be the best shape? Sphere. Because sphere has one dimension, right? Right? If it's just only one dimension, it's easy for all the calculations and get all the quantitative data we need. How easy to make spherical shape from the apple itself? Is it easy to do? I mean, if you look at the whole apple, it looks sphere, but the issue there is it's not a uniform size, right? You have a skin, if you remove the core, there is a seeds inside. So we don't know what we are trying to measure it here. It gets more complicated. So spherical shape, even though it's a uniform, single dimension, it won't be advisable to make the spherical shaped sample from the apple core itself. You can do cubical, but the issue there is it's 3 dimensions, right? Say it again. Yeah, you can make uniform size, but still the cubical sample will give you 3 dimensions, right? Then you really need to study the you need to monitor the deformation in other directions when you do uniaxial compression. So even though you can still do that, it became little more complicated, right? Cubical sample. Even though you can make the cubical sample, but it's three-dimensional study you need to do. So what's the compromise here? You cannot do sphere. You don't want to do cubical. What's the next option we have? Cylindrical sample. Cylinder has two dimensions. So you apply force in one dimension and you can monitor the deformation in the other dimension. So that is why when you look at the studies on mechanical properties, people always do the cylindrical sample. And also cylindrical samples are little bit easier to cut. You just need to have a cylindrical core and you poke it in and you can take the core out. And from there you can remove all the skin out, because when you try to put a cylindrical core into it, what you get is you get only flesh of the apple or potato or anything like that, or banana like that. So you can get only the flesh of the sample, because that is the core, that is the main thing we want to study, right? Because skin is something is different. We don't want to include skin and also the flesh. We just want to study the flesh, compression testing of flesh, apple flesh or banana flesh like that, right? So that will be easily reproducible, representative sample, right? So when you want a representative sample, cylindrical sample is the easiest way to make or take it out, and then we can do the testing. All is with me? So that is what we are going to do when we do actual practical demonstration. Not today, maybe tomorrow is Tuesday, maybe we will do some type of practical demonstration on uniaxial compression on Wednesday evening. So that's a plan. So we'll see how far it goes. Any questions on that? So here then we use the stress and strain are used. Yes, ma'am.
That the cylindrical shape, is it used for all kind of food material, like only is it only for fruits, or it is for all kind of food material like cake, biscuits, everything?
Very good question. The question is, can we use the cylindrical sample for any type of food material? In my opinion, we can use cylindrical samples if we can take a core of the cylindrical sample. We can do that. But at the same time, if you have other materials, we cannot make a core of cylindrical sample, then you need to think about other ways to do that. That's a very good point, right? Sometimes we may not be able to do for all the materials, but as long as we can have a representative samples, then we are good to go. So if you look at this shape here, if you take the cylindrical sample and then you apply the force, then you can study the force with respect to deformation. Make sense? So this is force, and then deformation is going to be here. So initial height is h, and then this is delta h, and the force is here, and this is the area you are applying. So when you compress a sample, what you get is the force and deformation. That will be your raw data in your testing, right? You will be deforming the sample and you will be measuring the force. So when you do that, if your typical curve would be something like that. Can we use this force deformation data as it is? Madam? Okay, we have to convert this force deformation into specific property. Okay. Can you expand that on? Can you expand more on that? When you say specific property, okay, okay, okay. We are jumping the gun here. We don't want to jump like this much because we will talk about that when we do the texture profile analysis. Okay, but here the force and deformation. Let's say my lab, I am doing the. My lab has my lab. I get potato sample. Okay, and then there's another X lab. They also get the potato sample. Okay, and then they are also trying to collect the force deformation data. Okay, so they collect force deformation data, I collect force deformation data. Can we use our force deformation data and compare our sample with the X lab sample? Can we? Okay, what would be the protocol my lab and the X lab have to follow? Sample dimensions. Okay, so if we both use the same sample dimensions, then we are good to go. Same sample dimensions, then the force deformation data will be good to use it for comparison purposes. Okay, if I do not know what sample they used, what dimension of the sample they used, what else, how else I can convert this data so that I can still compare my data with their data? Pardon me? Calculating the, your name? Ashish is thinking that because we do not know the dimensions of other labs samples, we may not be able to use the same dimensions. So we will be using different dimensions and they will be using different dimensions. So in that case, we just need to account for our dimensions in our test so that the final result can be compared between two labs. And that's what Ashish is thinking, that we have to convert this data. Instead of using force as it is, we have to convert this force with respect into stress and then deformation into strain. Make sense? So using force as it is, force deformation data may not be correct way to approach it. It's always good idea to convert that into stress and strain, and in that way you already accounted for your sample dimensions and your results can be compared to their results. Everybody follow that? So it's always good idea to convert your data into stress and strain and then use the stress and strain data for further analysis, representations, whatever you want to do with the data. What other information we need to be considered here? Anything else? When you think about this test itself, what else we need to consider here? Well, those are all variables. With I think somebody was saying about the moisture content, but that is something we cannot control, right? If sample has some moisture, it has its own moisture. We cannot really control the moisture as it is. Like for example, my sample has 20% moisture and their sample has 50% moisture. We cannot control the moisture, right? One thing they can do is they can dry the sample, reduce the moisture content to 20%. Correct? In that process, what we are doing, we are modifying the sample itself. My 20% sample, it's a natural sample. I didn't do anything with that sample at all. Their 50% sample, they may have to dry it out to 20% sample. So when you process it, then your sample structure modifies, everything gets modified because you are artificially adding additional process. So that may not be right way to do that. Okay, other parameters. Yeah, age of the sample also we do not know. Right? I mean, if I collect different age sample and they collect a different age sample, then it's okay. Those are all factors we need to consider. But I am talking about the test itself. Again, we are talking about the sample only. I am talking about the test itself. Some parameters we need to be constant, but that what kind of parameters we need to make?
The probe which we are using.
Okay, so assume that we both are using the same probe. Whatever diameter probe is same probe. In fact, we don't have to worry about what probe they use, what probe we are going to use, because we are converting everything into the stress and strain data. Yeah, but again, the deformation data we are converting to strain. So how much they deform doesn't matter for me, right? I can deform 50%, they can deform 20%. But at the end of the day, I am converting my deformation data to strain. They are also converting their deformation to strain. Well, penetration depth is same as deformation, right? How much you are deforming, correct? When you say penetration depth, are you trying to, you are thinking about putting a probe in thing and then penetrating through the sample? No. So penetration depth will be deformation. So we are already converting deformation to strain, so we don't have to worry about that. What else we
Suppose that temperature and time, sir, a particular a certain time, as we are giving for certain time this stress and strain, we are taking the data. How do we?
Yeah, but the time is already in the deformation. You are getting there, but what is the time we are talking about here?
The duration for which you are applying the stress. Duration.
Duration is right, but it doesn't matter. If I run it for 10 minutes, 2 minutes or 3 minutes, they run it for 5 minutes, they are going to get more data, I am going to get less data. But still stress and strain.
Time it is not losing its structural property, or we can say it is not till that time it's losing its elasticity till yield point.
No, that is always there, right? I mean, only so much we are going to compress it. After it ruptures, the sample is no more, right? We cannot use that sample anymore. That is given. But what other parameters we use to test the sample? There is one important parameters we all use during the compression test. You are applying the force, right? You are applying force. When I say applying force, you are going to compress a sample, and you are going to compress a sample at particular speed, right? The test speed also important variable. So if that lab is going to do the test and my lab is going to do the same test for the different samples, we should make sure that we both use the same test speed. Because if my lab run it at higher speed and if they run it at slower speed, the deformation, force deformation data will be totally different. So you want to make sure that you run the same speed for all your sample, because that will have a significant effect on your raw data you are collecting. So speed is important here. So make sure that you keep the speed constant and run the test. Any other questions anybody has? Yes.
So the texture property analysis thing, can we do, like we have to make sample of cylindrical, that is it, but what about some small particles like grains and flowers? Can we do that?
Okay, the question here is, for the solid materials we can get cylindrical samples. The question here is, can we do the compression test for the flowers and the small grains, things like that? Is it possible to do that? There are classical example for testing the powder samples, but that is not called compression test. That is primarily called about the how to measure the flow behavior. That's one thing, but that is totally different thing. We are trying to measure the you can add water, things like that, and then make the gel out of that or some dough out of that, and then you can do the testing on it. But that will be totally different than this test. The small grains, if you have a if you have a load cell which can take small amount of force, you can still do the actual grain as it is, but otherwise you won't be able to do that. Other test you can do is, you can take it in a cylindrical cup and then you can do a shear test also. So you can attach some type of this plate like that, and then you can shear the sample. That can be similar to compression test, but you are not really compressing it, but you are just shearing it. But you will still collect the similar data, force deformation data. So very good point. Other questions?
So in most of the research papers, they have taken cubical samples. Why is it like that?
Well, in my lab, we always do cylindrical sample only. The cubical samples still can be done, but depending upon how much, okay, the question here is, most of the research papers from her review process, they have done only cubical samples. What could be the reason? But it's just a matter of choice. I'm not sure how much they extensively they studied the data. They may just take the cubical sample and then do only uniaxial compression and then do the force deformation data and then calculate the stress and strain. But the issue there is, you still need to consider what happened to the sample on the other two dimensions. But only in cylindrical sample, it's easy to do that. Other questions?
How about disc-shaped samples?
Say it again.
Disc-shaped sample.
Disc-shaped sample? You mean small thickness sample? How small the samples you are thinking?
Like suppose chapati.
Oh, okay. Okay, in terms of the roti, chapati and all, then it has a different attachment to the texture analyzer. So basically, you can fit your roti and chapati into these two small plates. There will be a hole there. So you attach it there and then you force your probe into that chapati or roti, and then it will punch a hole and you collect the data. And from that you can analyze your data. So it all depends upon your sample you have, and then what kind of attachment you need so that you can measure the sample characteristics. Okay, we'll talk more on that. So basically, stress and strain. Stress is an intensity of force at a single point, and that's what the stress you can measure it. So force over area, how much force you apply divided by area, that gives you the stress. And in terms of the strain, it's a relative deformation, which is change in dimension to the original dimension. And that is what I provided in the previous case. So force over area, that is stress, and change in dimension over the original height, which gives you the strain data. So what is stress? Force is a mass into acceleration, and stress is a force applied over an area. So omega sigma is equal to force over area. That gives you the stress. One more thing is, it is not just your calculations, it's also important that you monitor the correct unit. So force is Newton, area is meter square, so you get Pascal. But typically for the food material, depending upon how big the sample is, it can go into kilopascal or it can go into the megapascal. So if you look at the data in the literature, lot of samples you may get in megapascal numbers. So you need to understand that also. You need to have appreciation for the unity here. The strain is nothing but the effect of stress acting on a material. So how much force you apply, stress you apply, corresponding strain you can calculate, which is initial height is h, and then when you deform the sample, this is delta h. So delta h over h gives you the strain data. So everybody with me? Stress and strain. That's more important than the force and deformation. So when you look at the solid elastic behavior, some of the material can be Hookean material, some of the material can be non-Hookean material. Within the non-Hookean material, some of the things can be non-linear elastic. So we are going to talk one by one now or discuss about it. So most of the elastic material, they follow the Hooke's law, that is from the law of physics. So force is a function of the displacement or deformation, and depending upon the constant of the spring, you get the constant value there, which is the spring constant, if you assume your material is purely elastic. In Hookean behavior material, you apply a normal stress, so you put the force on top of the material, force per unit area applied normal, which is perpendicular to the surface, and that's what the stress calculations you typically do. Force is F is force, area is A, and sigma is the stress. Different textbook uses different symbols, but as long as you are familiar with your own symbols, that's all it matters. You all know that what is stress and strain. Stress is basically how much force you are exerting, and toward the area you calculate the stress, and then deformation, whatever deformation happening because you apply your stress, how much of stress you apply, deformation will be different, and then you can get the strain from the deformation. So what area to use when you calculate the stress? We know stress is force over area, Newton per meter square. So unit is Pascal or kilopascal or megapascal. If it is area perpendicular to the force, then it's normal stress. If it's area parallel to the force, it's called shear stress. So if you take the sample like this and then apply the force over area, whatever you get is normal stress. And if you consider the area parallel to the force, so basically area under this parallel to the force, then it's called shear stress. So everybody with me here? Shear stress and normal stress. The shear stress, we can see this behavior when we do the practicum day after tomorrow. Even in pure compressive loads, there is still shear stress experienced. So when you compress a sample and when it breaks, typically it breaks in the intersection. It is always break like here. Primarily because when you compress a sample, there is more shear happening within the sample than pure compression itself. So actually I will explain to you. You will really monitor this when we do the actual compression test. So I'm sure you have done it. I don't know whether how many of you observed that, but it's always application of force, direction application of force. That's what makes the shear stress. So it's more shear stress happening in the compression test than actual compression itself. So most often failure in solids is due to shear stress when you rupture the sample. When you go that far, rupturing the sample, the shear stresses experiences are up. Shear stresses happens most of the time, and most of the failure occurring because of the shear stresses only, not compression stress itself. So now we talked about the stress. So in terms of Hookean behavior, normal strain, change in length per unit of length in the direction of applied normal stress. So force over area. So change in height divided by original height gives you the deformation. Deformation over original height gives you the strain, and that's how you calculate the stress strain value. So what happens when you are calculating in one direction? What happens in another direction? So this is called the longitudinal strain. Perpendicular to the force, it's a transverse strain. If it is parallel to the force, then lateral strain. Ratio between the lateral strain and transverse strain is called ratio between lateral strain and transverse strain, Poisson's ratio. So for every lateral strain, there is an accompanying transverse strain, and that's called the Poisson's ratio. And that is why a lot of times I tend to use the cylindrical sample, because there is only two strains here, right? If you use cubical sample, you have to calculate the another strain also, because we do not know when you apply. Let's say you take a cubical sample like this. It's not a really cubical. I'm not sure how I can erase that. Okay, this is probably more cubical than this one. So if you apply the force here, what happens is this dimension will be reduced, and this dimension also reduced, right? No, if you apply the force, this will be reduced and this will be expanded, and the other direction also get expanded, correct? So we will do example problem to do this, but this is what happens. So here you get three different strains. Make sense? Because three directions, so there should be a deformation in all three directions. So when you calculate the strain, you have to calculate the other all three direction strain, then it gets messy. You cannot really get the Poisson ratio calculations. Then you get two different Poisson ratios. Make sense? We don't want to have. So that's why typically I ask my students to do only the cylindrical sample instead of the cubical sample. Okay, let's look at the stress strain curve landmarks. So what you see here is the force deformation data for two different samples. So force, which is Newton, deformation, which is meter. Correct? We are following the consistent units here, right? Newton, meter. So when you apply the force, you collect the deformation, or you measure the deformation, you calculate the deformation, also measure the force. Then the force will be, the curve will be increasing. At some point, the force will be decreased and then start increasing. And that's called the bio-yield point. Not all the samples will exhibit this behavior. Some sample will exhibit this behavior, not all the samples may exhibit this behavior. And then if you keep increasing applying the force, you get the rupture. So no more, then once it go to rupture, then force decreases and it goes down, and then test is over. So if you look at this curve, and if you look at this curve, there is a yield point here, there is no yield point here. So this has a yield point, and this one doesn't have a yield point. Because we cannot expect yield point in all the sample we test them. It all depends upon what is inside the material itself, how the microscopically, structure-wise, how they get formed. So we cannot have the yield point for all the samples. What is bio-yield point? It's a point of microscale damage under small strain, and primarily because of the cell wall rupture. When we say cell wall, we are talking about the internal structure. You cannot even see anything. Nothing. When you compress a sample, small strains, small deformation, you won't see what is happening inside, but your data will exhibit that. So from this analysis, you can really tell that there is a micro scale damage under small strain. So basically it's cell wall rupture. It all depends upon microscopically how they are formed inside your material. Primarily these things happen for a natural products, okay, not developed products, or processed product. You don't see this kind of bio-yield point. The final is rupture point, point of microscopic damage under small strain, cracks, fissures and fractures. So if you have cracks, fissures and fractures inside the material, then macro scale damage occurs, and then the material ruptures and no more test needed, because there is nothing else you can monitor it here. The other important information, the yield strength, the strength at which the strain becomes plastic. Okay. Now we are talking about how the biological material will behave. If you look at this material itself, if you look at this curve, this is more of a linear, right? Initially, up to some point, it's more of an elastic material. How do we know whether it is, whether this point is yield strength point? We do not know until we do the unloading. Then if it comes back, follow the same path, both the loading and unloading, then it is yield strength. Most of the material will exhibit this type of transition point, where you can say this is plastic region and this is plastic region. So this is elastic, and after this everything is plastic. And then finally its ultimate strength or stress. So up to this point, this is called the ultimate stress or strength, maximum stress before it ruptures. So finally you can also get the deformation energy, and by area under the force deformation curve. So this is will give the total deformation energy. Different textbooks will give you different way of information, but these are the 4 or 5 different information you can collect, which will be more useful for comparing different samples. Every time we do the compression test, it's all about how you are comparing between sample to sample. These are all not absolute values for that matter, because we don't know what other people did, what test they ran, what type of sample they used. So this is just for your own sample only. Control sample is there, and then your treatments there. That is how you can do it. In fact, if you go back to your data and try to compare with other people, it won't compare. And you may be wondering what mistakes I made. They also did the same sample. At least they claim that they did the same sample. I followed their protocol, and my results are totally different. Your results should be different. So don't underestimate yourself. So don't think that, okay, whoever published the work, it's right work, and my work is not published yet, it's not a wrong. You cannot think that it's a wrong work. For all practical purposes, your result is your result and their result is their result. That is how you have to understand. Because no two results can be same, even if you use the same sample. Because depending upon what configuration they used, your configuration is different, so your results should be different than their results. Okay, there are other four important things I want to mention to you also. So going back to this same diagram here, so there is always linear limit there. So even small amount of all the samples will experience the small amount of linear limit. So that's what I have listed here, a proportional limit. So in this limit, what happens is loading and unloading will be the same curve. Both loading and unloading will be the same curve, and that's why it's called linear limit. So ideal solids behave according to the stress is equal to strain and the elastic modulus, but most of the time our biological materials are not ideal solids. So this is different than the ideal solids will behave. So here V means modulus. Sometimes people say Young's modulus, modulus of elasticity, Young's modulus or elastic modulus, you can name it whatever way you want to. It's just a modulus, meaning that ratio of stress over the strain that gives you the modulus. So it's a limited extent most solids will exhibit. If the curve is not straight, then you call it apparent modulus, because we are assuming our material is elastic material in that region. So you can call it as a apparent elastic modulus. The second is the elastic limit. So meaning that wherever it goes, loading and unloading along the same line, that's called elastic limit. So after the elastic limit, it's plasticity. So elasticity and plasticity. Here all the deformation is recoverable. So whatever you put energy, you can gain it back. Third one is yield point. It's also bio-yield point, rupturing of cell wall middle lamella within the inside structure. That's what I mentioned before. and slope of the curve changes from positive to negative. So if you go back to that slide, that's the yield point. This is the yield point. So you will get increase in strain even not without increasing stress. So material yields, that's what the yield point is all about. Usually it represents the microstructure failure, loss of strength, and then finally you get the rupture point and no more rupturing of epithelial vascular tissues. And again, as I said before, these are all for natural materials. For the new products we develop may not experience, I mean every material will have a rupture point, but they may not have a yield point. So in general, what are the information you can obtain? You can obtain the modulus of elasticity, which is slope of the linear limit, apparent modulus of elasticity, when is slope of the artificial linear limit. So you can calculate that based upon two different methods, secant method and tangent method. The stiffness is initial slope, and then toughness, sometimes people call it toughness, which is area under the curve until it breaks. So modulus of toughness, and finally the strain energy density, which is area under the curve. So if you have a stress and strain, so area under the curve here, that is the strain energy density. So this is stress and this is strain. Any thoughts on this unit? This area under the curve, how do you get into joules per meter cube all of a sudden? Energy to the volume, okay. Let's go back to the original unit, right? Original unit is what? Newton per meter square, and then divided by meter over meter, that cancels out, so Newton per meter square. So how this Newton per meter square becomes joules per meter cube? So you basically Newton times meter, meter square times meter, Newton meter is joules, meter cube. Everything coming from the base units. It's all about mass, kg for mass, distance for meter, time for second, like that. So everything comes from the base units.